Okay, I can't see you very well, but how many of you are scientists or engineers? Most of you. How many of you are still students but majoring in science or engineering? Okay, I agree that a lot of you probably already raised your hand. So there are a few lay people in the audience. Now, my next question I have to change after Dr. Ravi Bellamkonda's talk. How many of you were familiar with the term neuroengineering before you came here today? So I'd say about half of you at least. That's good. That's good to know. So I am a neuroengineer, as is my colleague Ravi there. I figured if I'm going to give a talk about neuroengineering, I better look up the official definition. And where do I go for that these days? Dictionary.com. No dictionary results. In fact, it might even be a non-word. Did you mean non-engineering? So, thankfully, Wikipedia has a definition for neural engineering, which is often used as a synonym for neuroengineering. And they say it's applying engineering techniques to understand, repair, replace, enhance, or otherwise exploit the properties of neural systems. So Ravi did already talk about some of the things I'm going to go into, and I'm delighted that he did that because I'm going to sort of give you a very big 30,000-foot overview of neuroengineering and skip over some of those things very quickly. So I prefer a shorter definition of neuroengineering, which is anywhere brains and technology meet. Or, yes, that's a microelectrode array that we use in some of our experiments in Dr. Gross's lab, which I'll be talking about in a moment. I prefer an even shorter definition, which you might have seen in the first slide, neuroscience applied. So in the same way that mechanical engineering and civil engineering are the applied versions of physics and mathematics, we could say the neuroengineers are taking neuroscience and applying it. Traditionally, engineers, as a lot of you probably know, traditionally engineers and scientists, especially neuroscientists, don't even talk to each other. They're two completely different cultures. They go to different conferences. They read different journals, very different cultures. And to name the overlap between the two made neuroengineering a legitimate field. It encouraged a new breed of interdisciplinary neuroscientists / engineers, or neuroengineers, to apply neuroscience and engineering principles to the making of devices that help people. And you saw some of those earlier. A little bit of the history of neuroengineering. So that word has actually been around since the 80s. I found the first use of it around 87, I think. Still hasn't made it into dictionary.com. What's the deal? The first conference was not until 2003. And in 2004, there were 2 journals created about neuroengineering. And in fact, we had an article in the first issue of the Journal of Neuroengineering of that year. But way before these 2 important milestones in the creation of a new field happened, a new research unit was created at Georgia Tech. So my colleagues Steve DeWerth and Bill Ditto had the vision to know that neuroengineering would be big. And they founded the Laboratory for Neuroengineering in 1998. Presently, the Laboratory of Neuroengineering has 9 faculty. So you heard from Dr. Bellamkonda. There's also Rob Butera, myself, Lena Ting, Bob Lee, Garrett Stanley, Steve DeWerth, Chris Rozelle, and Michelle LaPlaca. 9 of us all working at the intersection between technology and brains, where brains and where the nervous system and technology come together. So what does neuroengineering include? A variety of different things. Certainly, if you've been to the clinic to have a brain scan, you appreciate that there is now magnetic resonance imaging that can see the exact shape of your brain down to about a millimeter scale. Functional magnetic resonance imaging is not really being used that much in the clinic yet, but it will be, you wait. The idea is to probe people's brains by tuning this brain scanner to certain ways so that we can see which parts of the brain are active while you're doing certain tasks. And this has really helped us figure out which parts of the brain do what. So you often hear in news stories about this part of the brain lights up when you, I don't know, see one of Thad Starner's videos. And in fact, the brain cells don't actually light up. It's the picture on this brain scanner that lights up. But this has been very useful, and there's a lot of these types of brain scanners, PET scanners, CAT scanners. Somebody had to design, test, and improve these. That was neuroengineers who did that. Here's another one that you heard about already. The neuroengineering includes building sensory devices to restore some missing function. Here are two completely deaf people having a conversation without using sign language. In fact, over 200,000 people with cochlear implants who were previously completely deaf now can hear. This is the greatest success story of neuroengineering to date. Michael Korast, who's shown there, wrote a book about his experience of getting his cochlear implant called Rebuilt: How Becoming Part Computer Made Me More Human. It tells a very touching story of how neuroengineering technology transformed his social interactions, brought him out into the social world. Truly remarkable. So it's not just about understanding what people are saying, but as Sherry Turkle was saying, interacting with them with real conversations. Neuroengineering also includes smart prostheses to replace missing limbs. The new ones are controlled by neural signals directly. For example, Todd Kuiken at Northwestern University is transplanting nerves from the stump of an amputee to their pectoral muscles. And when the person thinks of moving their hand, these muscles are contracting, and they can put electrodes on the surface of the skin, pick up those signals, and use them to control the motors in the robotic hand. So all they have to do is think, like they normally would have before when they had a healthy, intact arm, think about moving their hand, and the robot just moves. This is now being used in a number of Kuiken's patients there. This is he's in collaboration with DECA Research Corporation. The DECA arm is probably the most sophisticated of these motorized robotic limbs there. Neuroengineers are also taking electrical stimulation of muscles in paralyzed arms and using them to reanimate those arms and allow paralyzed people to stand up, to walk, to move their hands. So you could say that neuroengineering is actually doing what we used to call miracles. It's making the deaf hear, it's making the lame walk, it's making the blind see even a little bit. The visual prostheses have a long ways to go before they're as good as the cochlear implant, but the cochlear implant had about a 30-year head start on that. So neuroengineering also includes, I talked about the clinical side, on the research side, it includes making devices to study the nervous system. And a lot of neuroengineering is being used to develop new tools and techniques that will allow us to understand how the nervous system functions and what's going wrong when it malfunctions. This is what my research group is doing at Georgia Tech. We build research tools such as cultured neuronal networks growing on these multi-electrode array culture dishes. So this is a network of about 10,000 rat neurons that we plated onto the dish. And these electrodes that you see in the nice hexagonal pattern there allow us to both record and stimulate those cultures. We use these tools, these cultured neural networks on multi-electrode arrays, to create a long-term neural interface that we can listen to the network's activity and also to send signals into the network and probe its function. And I had to put this picture up here to tell you this is what neuroengineers look like. They're perfectly normal-looking people. Most of them. In addition to electrical neural interfaces, we're also working on optical neural interfaces. So for example, this is a 2-photon microscope that we built that allows us to image these cultured neural networks continuously for days on end. This is something that you just cannot do in an animal. Most animals will not hold still that long on the microscope. We can watch them growing and forming connections. If you look carefully, you can see them reaching out, and they're actually making synaptic connections with each other while we're filming them here. We can also use high-speed microscopic imaging, in this case to look at calcium signals when the neurons talk to each other. So yes, calcium is not just for building strong bones, it's also a crucial element in how cells communicate with each other, and we can take advantage of calcium-sensitive fluorescent dyes to image these cells and look at the ongoing conversation that they're having and try to influence it with our electrical stimulation. Neuroengineering, as you saw in the very touching video, the fellow with Parkinson's disease, includes modulator devices to correct nervous system dysfunction, including deep brain stimulators. So these are helping thousands of people already with not just Parkinson's disease, but also dystonia, tremor, Tourette's syndrome, chronic pain, obsessive compulsive disorder, and most recently, really severe depression. Helen Mayberg at Emory is working on that. So it's been a fantastic boon to those people with those neurological problems. But there's one problem that hasn't really helped yet, which is intractable epilepsy. There are about 1% of the population has epilepsy. And there are a certain fraction of those people for whom anti-epileptic drugs just don't work at all, or they work very poorly, and they are faced with an option of living with the epilepsy or going in for brain surgery and having a substantial chunk of their brain removed. You can imagine that there will be certain side effects from that. So, we're working in collaboration with the neurosurgeon and researcher Bob Gross at Emory to develop smart devices to treat epilepsy with microelectrode arrays. Our idea is to continuously monitor the brain state with these electrodes and also to use them to sprinkle a little bit of electrical stimulation near the seizure focus to keep it in a state where it's basically too tired to have a seizure. And if it's successful, it might make surgical removal of brain tissue unnecessary. This idea came from our work in vitro, our cultured networks, which invariably develop seizure-like activity patterns. They've been cut off from their normal sensory input, and the tissue, like you, if we were to put you in a dark room, you would go crazy after a couple weeks. These cultures develop seizures. And we wanted to study learning and memory in these cultures. And these seizures were getting in the way. It's basically the network is incapable of processing information or remembering anything if it's having seizures all the time. So we developed a technique to quiet these seizures down. So here you see recordings from 4 of the electrodes, and these spikes, these rainbow-colored spikes, are these synchronous bursts of activity where the entire network is going at the same time. And at this, if I can get the right light pushed, at this moment here, we turned on our multi-electrode stimulation, which quiets it and levels it down. Here's another way to look at this. This is a video from my grad student, John Newman. Here you can see epileptiform activity patterns in the cultured network that were evened out after we begin to play sort of a melody of stimulation to the cultures, and he put some music to the sound of the stimulation here, which is kind of cool. So those are those synchronous bursts of activity that are pathological. And right about now, he turns on the stimulation. And you can see that it's just leveling out the activity and keeping it at an even keel there. So Bob Gross is hoping to apply this to his patients with intractable epilepsy. We're testing it out in his lab right now with rats. We have some promising preliminary results, but there's a lot of work yet to be done. So microelectrode arrays can be used both to stimulate and to record, but the most effective treatments will be closed loop. And what do I mean by that? I mean, if we have devices that are continuously monitoring the effects that they have on the brain, they can be continually tuning their output, their stimulation, to produce the optimum benefit. You could think of this as being like the way your car continuously adjusts the ignition and the fuel injection for different driving conditions, different speeds and whatnot. So these would be so-called smart neuromodulators. Currently, the present neuromodulators, the DBS systems that are being used, are dumb. They just keep stimulating. As long as that guy has that switch turned on, it's just going bzzz all the time, continuously. And so with traditional DBS, there's a lot of room for improvement. And we think that by making these things closed loop and adjustable and responsive, they will be more effective. There are a lot of other ways that neuroengineers are allowing us to interface with the nervous system, to influence and improve it, including magnetic stimulation. There are such things as transcranial magnetic stimulators that you can put just next to the scalp, so this is non-invasive. Send in magnetic pulses, and this is already being used to help people with depression. You heard about haptic and non-invasive interfaces from Thad Starner, and you might have heard recently about the Google Glass project, which is, I suspect, something that he started. So you don't need to put electrodes into the brain to interface with it. You can use the sensory and motor systems we were born with, our eyes, our hands, our ears, to connect high-tech devices to our brains. For a long time, that's going to be the most effective way to do brain interfaces, is through our hands, through our eyes, through our ears. Another one is optical recording and optogenetic stimulation. So with clever tricks with genetic engineering, you can make brain cells light sensitive, and someday we will have fiber optics implanted in our brains to stimulate and to record their activity instead of using electrodes. Genetic and tissue engineering. So Dr. Bellamkonda didn't talk about it, but he's also building scaffolds, for example, for the spinal cord to regrow across if it's broken. So there's a lot of tissue engineering going on to help various neurological problems. And another thing on the horizon is microinjection and controlled release of drugs. You can imagine most drugs are taken systemically. You take a pill, maybe you get an injection. When you do that, it's bathing your entire physiology with a drug that you really only need in one small part of your brain, probably. This is going to create a lot of side effects, always does create a lot of side effects that most of the users don't want. So you can imagine if we had microinjectors placed in just the right place, releasing the drugs, they would be more effective and have fewer side effects, especially if it were a closed-loop scheme where the drugs were released when they're needed or when the patient pushes a button saying, I need more of that, in an on-demand fashion. All of these are being tested in the lab right now, or in the case of Thad Starner, on his brave graduate students. And they're going to move into the clinic in the next decade or so. That's something that I feel confident about because they're already in clinical trials in some cases. Once they prove to be safe and effective for patients with various neurological disorders, what's going to happen? Normal, healthy people will begin to use them. So the next wave for neuroengineering is human augmentation. For example, so you heard about DBS, deep brain stimulation. Here's a quote from a Belgian patient with a deep brain stimulator that was implanted to help her with obsessive compulsive disorder. Her DBS electrode has, her implant, each one of these electrodes has 4 electrodes on it, 4 contacts. And she has one of those controllers that she can use to change which one is being stimulated. And she says, well, doctor, when I'm at home doing my regular things, I prefer to have contact 2. But if I'm going out for a party where I want to be on and, I'm going to do a lot of socializing, I prefer contact 4. Because it makes me revved up and more articulate and more creative. So people are already using neuroengineering to sculpt their own emotions, their own personalities. Also, another one that I've heard about, some DBS patients have noticed that brain stimulation enhances their memory recall. They went into the doctor because they have Parkinson's. They implant this device and they say, well, it's helping me with my tremor quite a bit, but I also remember things so much better than I used to. So here's a hard-hitting quote from Ramez Nam's excellent book, More Than Human, Embracing the Promise of Biological Enhancement. He says, in a world where we can sculpt our own emotions and personalities, people will no longer be able to say, I can't help it, it's just the way I am. That won't be a valid excuse anymore. So this technology has a lot of ethical implications, and neuroengineering gives us unprecedented control. Nam's theme is the sooner we realize that human augmentation is inevitable, the more we can head off potential problems of the past by thinking very carefully about how to proceed with these technologies. So now, back to the 30,000-foot perspective, why is neuroengineering or applied neuroscience so important? I think it's the most important thing. Maybe those are my delusions of grandeur, but because the nervous system controls all human behavior, the nervous system is where our memories are stored and played back. It's the master gland. It controls our hormone systems. It's what we use to make decisions. It's how we communicate. It's where our ambitions come from, our motivations, our emotions. It's, in some sense, where our self, our individuality comes from. With neuroengineering, we can change ourselves. We can change human nature. This has never been possible before. That's why it's so important. But that's just one reason why it's so important. That's not all. The next wave after augmentation, neuro-AI. So this talk has been mostly about neuroengineering as helping us to understand the nervous system with research devices and to use that understanding to build more devices that will improve nervous system function. Suppose that we use it instead to build smart devices for different purposes. Neuroengineers can help to remove some of the A from AI and make artificial intelligence less artificial. Why not take what we're learning about how the brain processes and stores information and apply that to artificial intelligence? Brains are very good at doing many complex tasks that demand real-time performance. Presently, digital computers like this one are not very good at that. Perhaps we can emulate some of the brain's tricks in some of these artificial systems, for example, the future smart grid. My group is working in a collaboration with power engineers, Ron Harley at Georgia Tech and Kumar Vinayagamurthy at Clemson University, to devise neurocontrollers for the future smart grid. Controlling power is only going to get harder and harder as more of this green energy comes in. Windmills, wind turbines, and solar panels have a fluctuating supply of electricity. So we're experimenting with using artificial neural networks to predict and to compensate for these fluctuations. We hope that by incorporating more biology into our artificial neural networks, they will become more capable at controlling complex systems like the electric power grid. There's a lot of work to be done. Actual deployment of biologically inspired artificial neural networks into the field is probably at least a couple of decades away. In fact, with all areas of neuroengineering, we are held back by lack of understanding of some of the brain's most basic operating principles. So this is my advertisement. Please vote for representatives who fund basic science research. It's important. I'll leave you with this image here. Neuroengineering today is where spaceflight was around 1865 when Jules Verne wrote this book. His idea was to get people to the moon by putting them in a big hollow bullet and shooting it out of a giant cannon. The tools neuroengineers are presently working with are that crude. 100 years after Jules Verne, what it actually took to get us to the moon was immensely complicated. The Saturn V rocket is full of complicated feedback mechanisms and complicated systems. Neuroengineers have just begun to build a few closed-loop systems, closed-loop brain interfaces. When neuroengineering reaches the Saturn V rocket level of sophistication, it's going to take society to new heights. It's going to hopefully cure diseases, change human nature for the better, and give us as much intelligence as we want, artificial intelligence and natural intelligence. Thank you.